Hey guys, I hope you're all doing good. In this video, I'm going to be setting up a pipe flow simulation using SolidWorks flow simulation. Okay. The reason why I'm choosing this particular problem is it actually helps you learn a lot about computational fluid dynamics. So to get started, what I'm going to do is I'm going to create the geometry in SolidWorks. There are certain things that you need to do in SolidWorks to run CFD. So in this video, I'll be paying attention to that. To get started, I'm going to click on the top plane and then I'm going to create a new sketch. Alright, so let's create a circle. So in this case, I'm not shooting for a particular geometry, I'm just eyeballing. So as long as it looks like a pipe, I'm good. Now, one thing you can do is after you practice this exercise, you can actually look up for accurate pipe flow geometries for which experimental data exists. You can run the CFD simulations and then compare the results with those experiments. That's a very nice exercise. And what I'm going to do here is I'm going to click on extrude and I'm just going to extrude it till 0.3 meters. Again, this is just an arbitrary length that I'm assuming. Okay, so that looks like a pipe. Then what I'm going to do is I'm just going to add a small thickness to the pipe. So I'm going to create on shell and then I'm going to select the top face and the bottom face. And let us see, maybe 0.01, so 1 mm. And let's take a look at the preview. That looks okay. So I'm just going to click on that and that's my pipe. Okay, so what I'm going to do now is I'm going to simulate the flow through this. So let us call this guy as inlet and then the other guy as an outlet. Now, when it comes to computational fluid dynamics, we are interested in simulating the flow inside the pipe. Okay, so what we need to do is we need to create something called as a computational mesh inside the pipe. And in SolidWorks, it uses an automatic mesh generation algorithm for which it requires that the entire solid is closed, also called as watertight. So in this particular case, I'm trying to simulate the flow through this pipe, correct? So the bottom, so the top and the bottom faces needs to be closed, okay? And how do you close that? You do that by creating something called as lids. This is specific to SolidWorks. So what I'm going to do is I'm going to go to flow simulation and you can see that there's this button called create lids. So I'm going to click on it and make sure that you select the face that you want to close. So in this particular case, I'm selecting this guy and you can see that it immediately draws this blue color shaded area. Now that's going to be the inlet of my pipe. Okay, you need a closed volume in order to create your mesh successfully. And similarly, I'm going to click on this face and then these are going to be my two lids. Okay, so when you rotate the geometry, you will see that these are closed. Now, if you pay attention and if you know a little bit about CFD already, then this is like a non-manifold edge. If you don't understand what that is, then don't worry about it. But basically, you need these lids to close the geometry. Now, different CFD codes have different practices, but the concept is you need a closed surface so that you can create the mesh either inside or outside the geometry. Okay, now once this is done, what I'm going to do is I'm going to set up the flow simulation. The easiest thing to do next is use the wizard utility. So let's just click on that. It's asking me to save the geometry first, so I'm going to save it. Maybe go to documents. Actually, you know what, I'll save it in a different folder. Okay, and I'm going to create a new folder called pipe flow. And let's just call it pipe. Okay, so launch the wizard again. So this helps you set up your CFD problem quite easily. And I'm going to call this pipe flow. With respect to configuration name, don't worry about it. We'll figure those out later. You can add comments in case you're interested. So click on next. Unit system, I prefer SI units. If you're used to some other unit system, go for it. Click on next again. So in this particular case, I'm interested in doing an internal flow, right? We are trying to simulate the flow through the pipe and not the flow on top of the pipe, right? If you have to do that, then that would be an external flow simulation. Again, don't worry, we'll be looking at those examples in upcoming videos. So internal, and then consider closed cavities. Don't worry about this option, leave it as default. We'll talk about this. All right, what are the physical features or what are the additional physics that we want to include in the simulation? Now remember that in computational fluid dynamics, whenever you include these physics, additional equations or additional terms or the way the equations are solved gets changed, okay? And we will be looking at those things in upcoming videos as well. So in this particular case, I'm not interested in heat conduction, so that's not checked. There is no radiation, so that's not checked. There's something called as time dependent, right? So I've not checked that. So what does that mean? So in a pipe flow, the simulation is what is called as a steady flow simulation. That is, after some point in time, your solution is not going to change with time. Now this might sound a bit funny to you if you have never been introduced to CFD, but the whole idea is at the end you get a solution that does not change with time. Okay, and that's what is called as a steady state solution. Now there are different ways to get to the steady state solution. It depends on how the equations are solved. We will be talking about those things a little bit later because those are slightly higher level concepts. So you need to know things like time integration or time marching in order to understand those terms. Okay, so in this particular case we are interested in steady flow simulations, and we are not going to include the effect of gravity. You can do that if you want to. And there's no rotation as well. So rotation is required in case you're trying to simulate something like a centrifugal pump. So moving on, the next thing that I'm going to do is define the fluid that is participating in my simulation. I'm going to be doing a gas flow here. So air is my working fluid. Just click on add so that it's getting added. Now in this particular case, the flow type is laminar and turbulent. What does that mean? Well, you are basically trying to tell SolidWorks what's your flow regime. Now, if the inflow velocity is such that the Reynolds number is greater than 5,000 or 10,000, you can directly use turbulent only. That is going to kick in the turbulence solver. If you're saying laminar, that means that the Reynolds number is really low. If you're saying laminar and turbulent, then the flow solver is going to be using computational models that are valid for both laminar and turbulent flows. Now we'll be talking about what these models are in later videos, but in general that's the idea. Now in this particular case, high Mach number flow, not really. I'm not going to do that. I'm just going to click on next. In addition to this, you can also add something called as surface roughness. So surface roughness is an important parameter that you need to include if your pipe is made up of something like cast iron. Basically the pipe is not smooth and hence it's going to cause additional pressure loss. Okay, now if you include a roughness height, then certain equations are solved which will basically account for this roughness and it would yield an additional pressure loss. Okay, so for now I'm not going to touch that. Just click on next. All the thermodynamic properties and parameters, they look fine. Here you can see that there is velocity parameters. You can initialize the velocity. You can say that at the start of the simulation the velocity is so and so, but in this case I'm not doing that. Similarly, turbulence properties, you can set up some turbulence properties. These things can be really important, but for us we are not going to worry about it. Like I said, these are things that we will slowly learn in the upcoming videos. Click on finish. And immediately you can see this box, right? Basically what SolidWorks is doing is it's calculating something called as a bounding box. It looks at your geometry. It looks at what's the minimum x, maximum x, minimum y, maximum y, minimum z, maximum z, and then it draws a box around your model. And that's what's happening here. Okay, so the next thing I'm going to do is choose boundary conditions, right click, and I'm going to type insert boundary conditions. Okay, so here what we're going to do is we are going to basically say that at this inlet the velocity is like 1 meter per second. So the first thing I need to do is I need to right click and then click on select other, and I'm going to select face at lid 2, and then in bracket you need to see pipe. Okay, make sure that you do not select this. You need to make sure that you select this. Okay, that is basically saying that at that phase the velocity is going to be 1 meter per second. So I'm clicking on that, and here I'm choosing inlet velocity, and let us say 1 meter per second. you're specifying the velocity magnitude here, okay, and you're not specifying the component of velocity. So if you have to do a 3D vector, then that will help you specify your x, y, and z components. So in this case, I'm just going to do 1 meter per second. Now, in addition to this, you can subject a fully developed flow profile at the inlet. So as you know, in a pipe flow, the velocity profile is going to look parabolic, right? I can enforce that profile by checking on this box, but I'm not going to do that. I'm just going to say that, you know, the velocity here is 1 meter per second. So that is what is called as a uniform profile. And as the simulation progresses, your boundary layer is going to develop, and we'll see that in the solution. And in the next phase, you know, let's just click OK here and do the same thing again. This time I'm going to right click on the other face, click on select other, and make sure that you select face at lid 1, and in the bracket you see pipe. Okay, so that's the name of your simulation, right? That's the name we gave initially. So you need to see that name, okay? Whatever the name that you gave, make sure that you see that. Do not select this option, that's the wrong one. In a later video, you know, I'll comment on why that's the wrong option. So for the outlet, what you need to do is you need to give a different boundary condition. Okay, so at the outlet, what I'm going to do is I'm going to select static pressure, and I'm going to say 101325. Now, if you're a mechanical engineer, then you might know what static pressure is. If you do not know, try to understand what static pressure is and what's the difference between static and total pressure. Now, with respect to boundary conditions, right? You know, you're solving a partial differential equation, correct? Now, for partial differential equations, you need boundary conditions. Now, the type of boundary conditions that you provide is very important. If you give the wrong boundary condition, then what's going to happen is the simulation is not going to give you the right results. It's going to try its best to get to the solution, but sometimes it doesn't. This is what you say as the solution is not converging. And typically the solution is not converging because the boundary conditions are wrong, or sometimes it has to do with your geometry. So in this case, you can see that I'm choosing a particular combination of boundary conditions. I'm using mass flow at the inlet and a static outlet. Okay, when I say static outlet, at outlet I'm providing a static pressure boundary condition. Okay, so that looks good. Let's click OK here. Now there is another boundary condition that we need to add, and I'm going to just select this guy, the wall, and let me just make this bigger so you can see what I'm selecting. Okay, I'm selecting this guy, and you can see that there's a small arrow there, and I'm going to say that this is a wall. Now there are several options. It says it's a real wall or an ideal wall. Okay, so here we are going to basically say it's a real wall. And you can see that there are additional properties such as wall motion. Again, don't worry about these things. We will learn them in upcoming videos. So let's say OK here, and that's basically it. Now we have almost set up our simulation. The next thing to do is to take a look at the mesh. Now, like I said, SolidWorks uses an automatic mesh generation algorithm. So what you can actually do is just right click on mesh, and it says show basic mesh. Now you immediately see the cut plane here, which shows you the mesh size. Okay, so this is basically what you call as discretization, and you can see that the discretization along X, Y, and Z direction is the same. So that is why the element looks like a square. It is possible to stretch out the elements if you want to. So in this case, you can also right click and select, not here, sorry, you can right click on global mesh and click on edit definition, and you can just change this initial level of mesh, and you can see that immediately the mesh becomes finer, right? So if you're using a larger number, you're going to have more mesh points and you can expect an accurate solution. Now we are going to start with a smaller value. So here you can see that SolidWorks provides us a recommendation. It's the initial level of mesh is set to 3. This is going to give us a reasonable solution in a reasonable time. Now in addition to that, you can do something called as an advanced channel refinement. Now when I click on that, nothing happens here, but what that does is near the wall of the pipe, it refines the mesh. Now here what you are seeing is called as an hexahedral mesh. So what does that mean? Now here you can see that along X, Y, and Z, your mesh looks square, right? Which means in 3 dimensions, it's going to look like a cube. Now that is what is called as an hexahedral mesh. Hexahedral meshes can be generated very easily by using something called as a binary tree or an octree data structure approach. Okay, and we'll be talking about these algorithms a bit later. I'm not going to be talking about them in too detail because this is still an introductory class. All right, so now that we have visualized our mesh, let's click on OK. And we're almost set now. So one thing I can do is I can actually run the simulation. And to do that, all I need to do is just press this run button here. And I'm going to run this thing in parallel. Okay, so I'm going to be using all CPUs. Now the default option is use all. Now if you don't have multiple CPUs, that is if you're using a really old computer, then you will see only this option. So let's click on use all and then click run, and that's going to run the simulation. Okay, you'll see a window like this. You can see that the calculation is going on about 49 iterations. You get the answer. Okay, so I'm just going to close this guy, and what I'm going to do now is I'm just going to try and visualize the results. So the first thing I want to do is I want to just hide the computational domain. I don't want to see it. Then I'm going to click on flow simulation, and then I'm going to set up a transparency for the pipe, so that I can see what's going on. The next thing that I want to do is I want to see the mesh inside the pipe, and the way I can do that is by clicking on results, and then what I'm going to do is I'm going to create a cut plane. So let's click on this cut plane here, right click on insert, and you can see that this is the XYZ plane that I'm selecting, and you can see that this green plane is basically cutting the pipe right in the middle, right? That's exactly what I want. And we are going to display some contours. What are we going to look at? Let's look at velocity first. Velocity magnitude, and I'm also going to be looking at the mesh because we want to see how the final mesh looks like, and the mesh is going to be colored in black. And let's click on OK here. There you go. You can see that you have a very funny looking simulation, but that's fine. Okay, the mesh is really coarse, and what's happening is you can see that initially the velocity is all uniform. Let me just put this in straight view. The velocity is initially uniform, but then there is something that is close to what you would call as a boundary layer, and that's going to make the mesh look more parabolic. All right, now again, this simulation is a fairly coarse simulation, and it looks like it did not do the channel refinement that I expected. So let me do something else here. Click on edit definitions. And what I'm going to do is I'm just going to refine the mesh maybe 2 levels more. And I'm just curious why it did not do the advanced channel refinement. That's okay. So let's click on OK now. And let's run the simulation one more time. I'm running this as a new calculation. I'm clicking on run. You can see that it's doing the mesh. I had about 25,000 mesh elements initially, and when I click on this information button, I can see all the details. You can see that we are running at 19th iteration. Things are a bit slow because now there are more cells. All right, perfect. So the solver is finished. So let's close this guy. Okay, so when I click on show again, this time, things look much more interesting. All right, so I'm going to select this guy, edit. Maybe what I'm going to do is just increase the maximum to 2.5. Actually, the maximum velocity is 1.3, so I'm going to set it to that. And let us see. For the color palette, I'm going to just increase the number of levels to maybe 15. Click OK. Yes, that looks much better. And I believe the flow comes like this. Yes. No, actually the flow comes from left to right. Sorry about that. Right, so you can see that the initial velocity profile looks uniform, basically along the x direction. Okay, so if you look here along the x-axis, the velocity is given the same color, right, which means it's uniform. And as I move from left to right, you see the boundary layer appearing, and then you are getting this parabolic profile. So the next thing that we are going to do is we are going to make some line plots and look at this parabolic profile and get some results out of it. Okay, so and I'll be doing this in the next video. I hope you enjoyed this video. If you have any questions, post them in the comment section. I would be happy to answer them for you. All right, I'll see you guys in the next video. Bye.